Okay, hello everyone. Welcome to the lecture. Please confirm me that you can hear me clearly and you can see my screen. Okay, thank you. Thank you. Okay, so for what was this? Class participation form 6, which was actually due on Sunday. So you guys have submitted it, but when I went through it, I saw that many students they have not responded to question number 2. Uh, but I would like you to at least write the questions which came to your mind while when you were watching the lecture, right? You can skip question 3 or you can keep it empty because question 3 asks about it wants you to write the statement of the question you asked, and since it was a recorded lecture, it is not possible to ask the questions, right? So you can keep it empty, or you cannot if you don't need to respond to it. But I want you to respond to question 2. So that's why I have extended its deadline to this Friday, 3 p.m. So please make sure that you go and update your response there. Okay. Uh, okay. So last time what we covered about what we covered was basically and when I say last time, it's mean the recorded lecture, right? So we covered the out of order execution and how reorder buffer is used for that purpose. But however, before that discussion of reorder buffer, we were talking about, if you remember, we were talking about privilege level switching, and one point or one thing in the context of privilege level switching was that how faults are handled, right? So prepared this slide and I wanted to discuss it with you. So I know, I mean, I am still far behind, but it's okay because you guys are reading the paper anyway. And once we are done with after the week 6, we will starting new paper, so it's fine. So uh, in privilege level switching, when, for example, if you remember, we said that whenever there is a hardware exception, for example, there is a if there is a page fault, then page fault basically happens when a user level program or okay. Before I start this slide, if you right now, if you have any questions about how the page faults are handled, please write them there. Write them in the chat. If you don't have a question, just write NP. No, 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 no question NQ actually. No question, no problem. Otherwise, write your question and then I will take care of them once I'm done with the slide. Okay. So page faults they arises when a user level process it is accessing its code or its data, and if you remember how when a program is executing, so memory is allocated to it, and how the memory allocation is performed by having this notion of virtual address space and physical address space, and then we have the page tables, right? So all the pages they need to be any page which a user level process need to access. It is first brought in from the disk into the memory, but it is installed in a frame, and then page table entry is reserved, which specifies that how the virtual page address will be converted or translated into the physical address, right? So let's say that you have a user level process running and a page fault happens. Page fault happens when, for example, a process generates an address, a virtual address definitely, and when the page table is looked up to translate that virtual address into the physical address, there is no entry in the page table for translating that virtual address corresponding to that virtual page, right? So why is it so? Because the physical page, the block of the data is not yet moved from the disk and not placed in the physical memory, and that's why there is no entry which the system can use to translate the virtual address into the physical address, and as a result, we incur a page fault. So when a page fault happens, So current execution stack, it becomes it cannot be used, or it is not reliable anymore, right? So by the way, page fault, it cannot be handled by the user level program. So page fault arises, or it originates in a user level program when the required page has no entry in the page table, but it can be handled only through the system level code, right? So let's say that when the page fault happened, so we have these were the values in our registers, like in stack segment register, stack pointer register, code segment register, and instruction pointer register, right? So we are indicating W and X in red color, just to indicate that W and X are basically pointing to this current execution stack of the user level process. And since there is a page fault, then this execution stack becomes it cannot be used, right? So which mean execution stack is basically it holds the information, it holds the temporary variable within the scope of the current user level process. So we cannot use this stack when the system level code is going to handle the page fault, right? So when the page fault when the page fault happens, so what happens is that each page fault is basically a type of an exception, and each exception or each interrupt has a number. For example, let's say I'm just building this number. So let's say that for page fault, the interrupt vector number or the exception number is 14. So uh, uh, using that number, you index into the interrupt descriptor table, or IDT, right? And then based on the index, you reach an entry, and this entry gives you certain information. So it gives you the handler instruction pointer register, and it gives you also the handler code segment register value. So what are these? Code segment register, a code segment value basically tells you that what region of the physical memory holds the code which is responsible for which actually which region of the memory holds the code which is responsible for running the code of exception handler. For example, in our case, page fault handler, right? And instruction pointer is basically, when how you get the address by combining code segment register and adding to it the instruction pointer register, right? So instruction pointer register is like kind of offset, right? So let's say that I'm just putting here some example values like P and Q, right? And the third field available is the IST index, interrupt stack, if I remember it correctly, interrupt stack table, I guess, right? So in this interrupt stack table, you have 8 different entries, and each of these entries basically hold addresses or pointers to 8 different stack structures in the memory, and these structures are maintained, or they are managed by the operating system, right? So for example, let's say the given IST index value points to a certain pointer SP3, which points as a certain pointer SP3, but we will see how it is used. But at this point, before we do that, what happen is that this P and Q, they are sorry, the stack segment is, as I said, since they are together, W and X are combined together to point to this the current execution stack, so they cannot be used anymore. So what happened that the stack segment is set equal to null, and stack pointer points to SP3. What is SP3? SP3 is basically this address. So what happens that stack segment and SP and RSP, they are combined together to reach the stack 3, right? So it will give you the access to a certain memory location which holds the stack 3, and then this stack will be used to copy the all the values of all the registers. Remember, we talked about execution context, and what is the execution context? The execution context is the all the values of all the registers which are necessary to successfully run the program. So at the time when the exception happened, these registers had certain value, right? Certain value, which is basically corresponding to this user level program. So what we need to do that we need to store these registers in the stack, because when you will be running the page fault handler, it may override the values of these registers. That's why your operating system, at the part of page fault handling, it will first copy all these all these registers, values of these registers in the stack, in stack 3, or any stack which is pointed by uh, this field in the entry, right? And then the code segment and the instruction pointer register for the fault handler, they will be copied to code segment register and RIP register of your core or of your processor, and then they will be combined together and to generate a target address, which will be basically pointing to your exception handler routine. And then this exception handler routine will be executed, and once it is executed, once it is executed, during the execution, it is possible that it overrides these registers. That's why we have all the operating system will save them in advance in in stack 3 or in a memory region. And once the execution of the exception header routine is completed, the last instruction will be I return or interrupt return. And when this execution is executed, as a part of its execution, the what happens is that these registers, all of these registers which you saved earlier in stack 3, they are restored, their values are restored in the respective registers. And then the control returns to the same point in your user level program where page fault handled. So now, and then the next instruction will be executed in the user level process, right? And as a part of that, your these values W and X, which were actually saved in stack 3 and then restored in the registers, they will be placed back into your SS and stack pointer register, so that it will be now pointing back to this current execution stack of the user level process. Okay. Let me see if there are any questions. Okay, everyone says no questions, but are there now any questions after I have covered the slide? And by the way, are there any questions related to that recorded lecture? If you have any questions related to that recorded lecture, you can ask them now. Out of order execution and how reorder buffer is used and reservation stations, renaming, so on. Can you briefly explain the IST index again and the IST? Uh, Yeah, so IST is basically it is interrupt stack table. So it holds it has like in this example it has 8 entries, and each entry contains a pointer. Pointer is basically an address in the memory location, right? So basically, what it each pointer is pointing to is a stack data structure. So for example, this SP3, it points to the start of this stack 3, and SP0, it points to the start of the stack 0, and SP7 in the same way will point to the stack 7. And the purpose is why operating system is maintaining these different stacks, because the current execution stack is indicated how you can access a stack. So for accessing the stack, you need to combine the stack segment register with the stack pointer register, and by adding their values, what you will get a memory address, which will be basically pointing to a stack, right? So the current values are pointing to this, were pointing to this, the execution stack of the user process, which mean that it had some values. It had some values which were basically the local variables of that user level process, right? So we cannot use this stack because it is a user level process. We don't want to we don't want to override those values. So what we do is that operating system maintains different, like for example, 8 different stacks, and one of them is selected. And during the execution, what will happen? What is the purpose of the stack? That the all of your execution context, it will be saved in the stack. before executing this code of the exception handler. And once you are done, which is indicated by executing the I return instruction, interrupt return instruction. So these values which were stored in the stack, they will be which were stored in the stack, they will be reloaded or restored in the registers. Right. So the basic purpose of IST is to help in storing the execution context uh, of the process which is interrupted as a result of your page fault, for example. Okay. Is there a limit to how much a processor can multitask in a single cycle? Quinn, is your question in context of like previous lecture, out of order execution? Okay. Is there a limit to how much a processor can multitask I think by multitasking, what do you mean by multitask? You mean to execute two different threads at the same time?
I just noticed that in the simulation, the there was like a lot of things happening at once in a single cycle, like the fetch decode and then the execution of each instruction. So I was wondering how if there's a limit to like the amount
Okay,
of
okay,
different things that
okay,
could happen.
okay, I got it. So by multitasking, I guess you mean that how many different instructions can be in different stages of the pipeline at the same time. For example, let's say instruction A is in fetch stage, instruction B is in decode stage, instruction 3 is in, let's say, execute stage, right? Are you asking that? Yeah.
Yes.
So if you are asking, in other words, you are asking that how many instructions can be in the pipeline at the same time. So it depends upon how many stages of the pipeline you have. One thing. So this is like basic thing, like if you don't add any other complexities in the picture. So if everything is straightforward, and then the number of instructions that you have in the pipeline at any given time or in a single cycle, it depends upon the number of stages. So if you have four stages, you can have four instructions in the pipeline in the same cycle. If you have five stages, you can have five different instructions, one in each stage of the pipeline in the same cycle. But then there are issues like, for example, if as you have seen in that lecture or simulation, like when a previous instruction, sorry, a younger instruction is, let's say, dependent upon a previous instruction. So it is like, waiting for the previous one to produce the result, right? So it cannot proceed. So if, like, let's say if you have four stage pipeline, and ideally you can have four different instructions, you can have four different instructions in the pipeline, but let's say second one is dependent on the first one, and third one is dependent on the second one, and the fourth one is depending on the third one. Now, yes, all of them can be fetched and all of them can be decoded, but then other than the first one, all three will be like waiting for the first one to complete before they can proceed to the next stage, which is execute in context of, for example. Okay. Uh, is there a limit to how much a processor can multitask? Okay, I think I answered that. I think Eric is answering to someone else. Okay. So is there anything else, any other question? Okay. So other than out of order, remember we said why we are using out of order execution. We are using out of order execution because there is a performance gap between a speed gap, let's say, between your processor and the memory. And what we do is that we want to bridge that gap. Sorry. Okay. So there is a speed gap between the memory and the processor, and we want to bridge that gap. And there are different ways you can follow to bridge that gap. One of them is like doing the caching, or the other is out of order execution, and that's yet another way is speculative execution, right? So the speculative execution, it appears or it manifests itself in two different forms: conditional branching and prefetching. So what is conditional branching? So conditional branching happens when in your program you have a sequence of instructions, and so like for example, if you have an if else, right? So if you say if uh, let's say condition X. So if condition X is true, uh, I'm just writing T. So if condition X is true, do a set of statement, S1 set of statement. Else, execute, I'm just writing E for else, execute a second set of statements, right? And when I say second set of statement, it can be any number of statements, like maybe 5 or 10 or 2, whatever, right? And same is true for set S1, right? So uh, conditional branching is like now let's say that let me go back to the to OneNote, and then I can, because it's a bit hard to write here, and I think I will need to write a good amount of text, so it's better if I go to OneNote. I don't know, let me create just simply a new page. Why I cannot create a new page? Okay. So yeah. So let's say that let me restart my OneNote. I think there is something wrong. Don't want to waste time, and let me give me last try. Okay. Sorry for wasting your time. So yeah, suppose you have this code. If condition one is true, and then do this setup statement S1, else do another setup statement S2, right? So What is the issue with conditional branching? So let's say C1 condition is something like, uh, for example, uh, if memory location X is equal to 10. So you are saying read the data from memory location X, and if it is equal to 10, then execute set of statement S1, otherwise execute set of statement S2, right? Okay, again, sorry, I again forgot. Please write any questions if you have about conditional branching, okay? I will take care of them after covering the slides. So now, this memory location X, so you are basically first reading the data and you will bring it into the register, right? So where is the data? Data is in memory, right? Data is in memory, and processor, you need to first bring it from the memory into the CPU and put it in some register, right? And then you will compare it with 10, right? Now, uh, but you don't know how long it will take to read the data from the memory. So it depends. If the data you are reading is in L1 cache, it will take less amount of time. If in L2, it will take more time. If in L3, even longer. And if it in memory, it will be super slow, right? So since we don't know and we don't want to waste our time while we are waiting for the data to become available in the register, so what do the people propose? They said, okay, instead of waiting for the data to become available and then do the comparison, we can do the prediction, right? So prediction that the data which will be fetched from the memory, we are predicting whether it will be equal to 10 or not. Now, when you are predicting, you can do two prediction, like it will be equal to 10, the condition will be true, or it will be not equal to 10, the condition will be false, right? So if you are saying the condition, if you are predicting, uh, your prediction is uh, condition is true, right? So it's mean you are saying this branch, this set of code will be executed, right? And if you are predicting the condition will be fast, then S2 will be executed, right? Now let's say our prediction is that our prediction is that the value which will be brought in from memory will be equal to 10 and condition will be true, right? So but we don't know yet, right? So what you do is like you start executing this code, right? And but what if you remember from the previous lecture, so these instructions in S1, they will produce some data, some results, right? So but those results, they will be written in reorder buffer, if you remember, right? For example, destination register value. So those results will be written in the reorder buffer, but not in the register file, or not in the register alias table rat, right? So when will be those results written in the register in the RAT? When we actually get the data from the memory here, right? And let's say the value is V, and then we compare. Once the value is in the register, we then do the actual comparison and compare it with the 10. Now we predicted, what was our prediction, that it is true. Now what is the come out sorry, what is the actual result? So there are two cases, right? So let's say the actual result V is equal to 10, right? So it's mean our prediction is true. If our prediction is true, we can simply write all those results back into the register file or RAT, right? But if V is not equal to 10, then it's mean that our prediction is false, right? So if our prediction is false, it's mean that all these instructions which were executed here, right? They were executed speculatively. Speculatively mean that we just made a speculation that our condition will be true, and based on that speculation, we started fetching the instructions from S1 and started executing them, right? But now it turned out that we made a misprediction, right? We predicted that it will be true, but actually it turns out to be false, right? So now what we need to do, we cannot write these results into the register. We simply flush all these entries which were corresponding to these instructions in the S1, right? So that is the idea behind conditional branching. or conditional branching and the prediction, right? So conditional branching, what function it performs? So branch instructions, they change the program flow, just I said, just like I showed you, like if or else, based on the condition. So like for example, implementing if statements and loops like while and for, right? Uh, the issue is that they create a problem for the decode stage, because if there is no branch in your program, what happens that all the instructions, they are executed in sequence, like first instruction, second instruction, third instruction, fourth instruction. But when you have a branch, so it depends. If condition is true, you will execute one set of instruction. If condition is false, you are supposed to execute another set of instructions. So like there is diversion in your execution flow, right? So that's why they create the branch instructions, create a challenge or a problem in the decode stage, as the next instruction to fetch is unknown until the branch condition is evaluated, right? But we cannot wait the branch condition to be actually evaluated, because what if the data which is involved in condition, for example, in comparison, you are bringing in that data from memory and it takes let's say it takes 200 cycles. Then if we keep waiting for 200 cycles, we are wasting the time, right? And that's why, as I said, people use the prediction. Modern CPUs use predictors to guess whether a branch will be taken, allowing the decode stage to continue speculatively on the predicted path. In our case, we said that condition will be true, so we will start fetching from we will start executing from S1. But if let's say the prediction was that the condition will be false, then the next instructions would have been executed from the set S2, right? The issue is that the branch unit checks the predictor's guess upon execution. Just like, for example, I showed you, like when the data is actually brought in the register, and if it turns out that we mispredicted, then all the speculative executed micro ops, they need to be squashed. And by squashing, we mean that we simply erase our how to say make the corresponding entries in reorder buffer as invalid, and we don't write their results back into the register file. And then CPU will then start fetching from the correct instructions. For example, if we predicted that condition is true, but actually it turns out to be false, so all those instructions which were executed from S1, they will be flushed or they will be squashed in the reorder buffer, and then the instructions from the S2 will be executed. Okay. Okay, do branch predictors create a scenario for both outcomes of the branch, or does it try and predict which outcome is going to be more likely? Uh, Actually, it is the second case. Like the branch predictors, they try to predict that which outcome is more likely, and based on the prediction, the processor starts fetching the instruction from that set of instruction, or from that target, like predicted target, right? Uh, what happens if the CPU guesses the branch wrong? Is it possible to have a wrong branch? Yes, it is. Actually, it is not CPU. There is a component in your core which is called branch predictor, which is responsible for making the guess or predicting the branch. And if the prediction is wrong, as I said, all those instructions which were like executed, remember from the previous lecture, uh, we do the execution, and then we write the results in reorder buffer, and then in the next stage, in W stage, we write the result in the registers or the memory. So when you are doing the speculative execution, which means that you did the prediction, and based on the prediction you start executing the instructions, you don't write the result of those instructions. You write the result of those instructions in the reorder buffer, but you don't allow that instructions to enter the W stage, which means you don't allow those instructions to write their results back into the register file, or in the memory, as long until your actual data is available. When I say actual data, it means the variable which you are comparing, the condition variable is available, and you can perform the actual comparison, and you know that whether your condition was actually true or not. So if your actual result of comparison is same as your prediction, you allow those values in the reorder buffer to be written in the register file. But if your actual result is different from your prediction, So you simply flush all the values or all the execution results from the reorder buffer. If the CPU keeps guessing branches to stay fast, is there a limit to how many wrong guesses it can handle before performance actually gets worse instead of better? Uh, it is Actually, there are different type of branch predictors. Okay, so each branch predictor, when like for example, different kind of branch predictors. So just like for example, let's say you have different sorting algorithms, right? I hope you have taken some courses on data structure. I hope I'm not making a mistake by giving an analogy of sorting algorithms. So all the sorting algorithms, they are doing their job is the same to sort your data, right? But some of them are more efficient, which basically mean that they are more fast as compared to others. Same is the case for branch predictors. So the job of all the branch predictors is same to predict whether a branch will be taken or not. However, some of them are more efficient, and here the efficiency is defined as that uh, how many of the predictions they made are actually turned out to be right predictions or correct predictions, right? So which basically mean that the lower misprediction rate is the criteria for comparing the branch predictor. Now, coming to your question, is there a limit to how many wrong guesses it can handle? Uh, so if like for example uh, your how to give you this example, how to answer to so if like you have more branch mispredictions as compared to the correct predictions, then it's mean that the loss of the performance you are getting from misprediction is higher than the advantage you are getting from the correct predictions, right? So like this is a uh, like very very layman understanding of at least to try to evaluate your performance of your branch predictor. So if there are more number of mispredictions or higher percentage of misprediction is higher than the number of correct predictions, then it's mean that your branch predictor is counterproductive. Okay, I hope I answer your question. Uh, okay, so now if you have any questions about prefetching, please write them here. I am covering the prefetching material. You can write the questions and I will take care of them after the slide. So remember, we said that speculative execution, it appears in two main forms: conditional branching and prefetching. I have explained the conditional branching, which appears when you have, let's say, a condition-based diversion of execution flow. Prefetching is not necessarily that. Prefetching is like what you do is like, for example, let me again go back to the to OneNote and try to explain it because it will be faster there. So prefetching is let's say you have you have an array of a data, right? And maybe let's say it has 0 to 1000 elements, right? And you are running a loop which accesses each element of the array and increments it by one, right? So now the data is, where is that data located? Initially, memory is source of all the data. So this array is in memory, right? So array is here in memory. Where is your core? It is where is your processor or core? It is on the chip, on the memory CPU chip, right? So you need to bring, like for example, if you want to access the first element A, right? So you need to first bring into L3, then L2, then L1, and then to the register. And then from register, the data will be accessed by your core, right? Or which is basically mean your execution unit or functional unit, right? So it takes time for the data to be read from the memory and moved into the register. So what is the objective here? That you have a circuitry which will prefetcher. It will actually monitor your access pattern. So like let's say if you are saying that all the elements are accessed in sequence, so first A, then B, then C, then D. So your prefetcher, it monitors the patterns, and if it finds that you are accessing elements in sequence, so then what it will do that when you are saying okay, fetch D from the memory, then it will say okay, now I know that the next element will be fetched is E, right? So while I'm fetching D, why should not I also fetch E, F, and G future elements or next elements? So and bring and place them in the registers in advance. And as a result, when your core will actually need that data, so it will be already available. So the thing is like you are start prefetching the data and bringing it in the registers of CPU in advance, so that you can hide the latency. Otherwise, every time when you like if you fetch only A, so first you need to wait until it becomes available in the register R1, and then you need to wait when an instruction actually asks for B, and then B is again brought from memory into the register, and then you need to wait, and then when instruction asks for C, you bring the C from memory into the, so it wastes your time, right? So this is called prefetching. Okay, so its goal is that in modern CPUs, prefetches they predict memory read patterns, and they load the data into the cache before it is requested, minimizing the latency for the predicted access. So again, here is again a kind of prediction is involved. The prefetcher will monitor the access pattern, and based on its monitoring, it will try to infer the information that what next element will be accessed, right? So in our example, we said all the elements are accessed in sequence, right? Another option, another situation will can be like where you are accessing every second element, right? Element 0, then element 2, then element 4, and so on. So then prefetcher will be able to infer that pattern, and will know okay, after 4 the next element need to be accessed as element 6, right? So the hardware circuit will monitor this memory access pattern, for example, sequentially reading an array, and when a pattern is recognized, the prefetcher will proactively load the next expected cache line. So what will be the benefit? The benefit, as I said, this if you successfully predict the read operations, your successfully predicted read operations will become much faster, because your required data will be already present in the cache. So it is like not like at the time when you ask for the data, it is not like at that time the data will be brought in. It will be already made available. Okay, so what challenges do you think we can have when we prefetch the data? Okay, let me answer your questions, and then I can ask you to answer this question. Okay. Why does the CPU use prefetching? So to hide the memory latency, as I just explained, if you bring the data one by one from the all the elements of an array one by one, then bringing element every element will means spending an extra spending latency or waiting for it. But if you are when you are bringing in A at the same time, if you say okay, also bring C and D, remember from memory into the cache and a single access, you can bring in 64 bytes of data. So let's say if you are now have an array of characters, so each character is 1 byte, right? So if you are not using the prefetching, so you will say okay, first bring the uh, first bring A, then B, then C, and so on, right? But if all of them are fetched in the same time, so like A, B, C, D, so in one cache line, how many characters you can have? You can have 64 characters. So when you bring in one cache line, you will bring the 64 characters. But when you are using prefetching, and you know that there is a long array of 1000 elements and all of them are characters, so you can say okay, first, you issue the request to bring in the first cache line, which holds the 64 characters, and then before waiting for the program to ask for the next 64, 65th character, prefetcher which will on its own issue the request of okay, also bring in the next cache line, which mean bring in the next 64 characters, right? And they will also be brought into the cache, and then made available when there is a space in register, right? So they will be bring closer to the core, like placed in the L1, and as a result, what will happen that the latency of reading the data from memory, it will be overlapped, or it will be reduced. Okay, so if spec why does the CPU use prefetching? If speculation later gets squashed after prefetch happens, the effect of the prefetch remains in the cache. Uh, yeah, so that is a very nice question. So Kevin, you asked a speculation. Let me, where is it? It's gone, I guess. Where is that? Yeah, what? No, no, where is that question? Yeah. If speculation later gets squashed after prefetch happens, the effect of the prefetch remain in the cache. As I said, it's a very good question. So why? Because when you do squashing, so you are squashing only the instructions in the pipeline, right? But which means you are erasing the result of uh, computing those instructions which were predicted actually, which were mispredicted, right? But prefetching brings in the data not in your pipeline. Prefetching brings in the data from memory into your caches like L3, L2, and L1, right? So the data remains there. And actually, there are some security attacks which exploit this fact that the data is left behind even when you squash the mispredicted instructions, right? And so, well, for example, Spectre, I think we will cover it in toward the end of the semester, in like last or second last week of the semester. We will cover the Spectre attack. So it basically relies on the fact that when you squash the instructions, they are flushed from the pipeline, but the data, for example, if as a result of executing those mispredicted instruction, if the data was fetched in the caches, that data still stays there, and an attacker can actually exploit that data to launch a security attack. Okay, if branch prediction is wrong, it can slow down execution speed instead of speeding it up. That's correct. Okay, I think that's a kind of comment, I guess. If you are bringing incorrect data into the cache, you are taking away space for. Oh, okay. I think you are responding to what are the challenges, right? Yeah, so that's correct. If you are bringing incorrect data into the cache, you are taking away space for actual useful. And why we will bring by bringing the incorrect data, which basically mean that, for example, I have a prefetcher and it says, okay, I detected a sequential pattern, like all the elements are accessed one by one, and but it doesn't know that how many elements will be accessed, right? So maybe in my program will access only 64 elements, but prefetcher is aggressive. It prefetches it prefetches starting from 16th element to 128, right? So all the elements which are accessed from 65 to 128, they are not needed. My program will not use them, right? But that they will pollute the cache, right? Okay. So that is like the one challenge. So and the other thing is another challenge of like prefetching is wrong timing. So if you prefetch too early, it can cause cache evictions before the data is used, right? And prefetching too late means the data isn't ready when needed. So let me also try to explain what we mean by this. So let's say you have this program. Let's say you are saying X is equal to array I. You are accessing ith element of array, then you are doing some code, and then you are going back. There is a loop, and then here you have a value of you have a for loop. I is equal to 0 to, I don't know, maybe 1000, right? And your prefetcher then monitors the patterns and it sees, okay, all the elements of array A are accessed in sequence, right? So let's say here this is the cache, right? And it when you fetch in A0, so it is placed, let's say A0 is placed here, right? And then it also fetches in A1 and A2, right? And but at this point only A1 is A0 is used, right? And then these instructions are executed. Let's say these instructions also bring some other data in the cache, right? Not the array data, but some other data, right? So they also occupy the cache space. So what will happen? Let's say they override this location, right? And now when you go back and you want to access A1, it is already overwritten, right? Because this is the problem. This is why what the problem is arising from the fact that maybe the prefetcher is prefetching the data too early before it is actually needed, right? The other issue on the reverse side or on the flip side can be like when you are fetching the data too late, right? So, for example, x is equal to ai here and only one instruction there, right? And or maybe only two instructions, and then you are going back to the loop, right? But after executing these two instructions, when you come back and you try to access A1, right? So it is not yet placed in the cache because it takes time, right? So prefetching too early and prefetching too late is a problem. So you need to like strike a balance. Accuracy versus coverage is the same thing which I explained earlier, and then a student said so. Like if you are prefetching very aggressively, it can pollute the cache by fetching the useless data. And the other thing is like it adds the hardware complexity. Why? Because there are different prefetchers for different, when I say prefetchers, different hardware circuits which are designed to monitor specific access patterns. Like for example, if you have a sequential access pattern, it will have one type of prefetcher. Maybe let's say if you have a strided access, like for example, you are jumping with but with a fixed amount of jump, like element 0, then element 10, then element 100, right? So you will have another kind of prefetcher. So for every type of access pattern, you will have a specific hardware prefetcher, which will increase the complexity of your CPU or your processor. Okay. If you're bringing, okay, okay. I think no more questions, right? Okay. Any questions about cache memories? So if you please write down all the questions you have about. Oh, sorry, why didn't you remind me? We have the presentation today. Okay, sorry, I should not blame you. Sorry, it's my responsibility. Okay, let me stop here. Let me stop here. And who is supposed to present today? Do you
I'm
want me?
done today.
Okay, so let me allow you to share the screen. Is it fine if I record your presentation?
Yeah, go ahead.
Okay, so I'm not disabling the recording, so you can share your screen and start your presentation. I'm muting myself.
Give me 1 second. All right. Good afternoon. My presentation is on Intel SGX, specifically sections 5.5 through 5.6. These sections focus on two main topics. The first is secure paging, which allows enclaves to work even when the protected memory is limited. The second is enclave measurement, which is used to verify the identity and integrity of the enclave. In this presentation, I'll explain the motivation behind these features, how they work, their contributions, strengths and weaknesses of the paper, and then some suggestions for improving it. Here's a quick overview of what I'll cover. First, I'll explain the motivation and the main problem the paper is trying to solve. Then I'll go over the core idea, which is secure paging. After that, I'll discuss the contributions and results. Next, I'll explain enclave measurement. Then I'll talk about strengths and weaknesses of the paper. I'll also briefly discuss why these features matter in real-world systems, and finally give some suggestions for improving the paper. Motivation and problem. Intel SGX enclaves run inside a protected memory region called the Enclave Page Cache, or EPC. The problem is that the EPC is relatively small. For larger applications, this protected memory can fill up quickly. Normally, when memory fills up, the operating system swaps pages out to a main memory or disk. But in the SGX threat model, the operating system is not trusted. That means the OS could potentially read, modify, or replay enclave data if normal paging were used. So the challenge is this: how can enclave memory be moved out of the EPC when space is needed without exposing sensitive data or allowing it to be tampered with? Another reason this problem is important is because SGX is often used in environments where the system itself cannot fully be trusted. For example, in cloud computing, applications may run or infrastructure owned by a third party. In those situations, even system administrators or privileged software could potentially access memory. Because of this, SGX assumes the operating system could be malicious and focuses on protecting data at the hardware level. This means that even something as common as memory paging becomes a security problem that needs a specialized solution. Secure paging. To solve this problem, SGX introduces a secure paging mechanism. When the EPC becomes full, enclave pages can be evicted to a normal system memory. But before a page leaves the EPC, the processor encrypts the page. In addition to encryption, SGX generates integrity metadata, including a message, authentication code, and version information. This prevents an attacker from modifying the page or replacing it with an older version later. When the page is needed again, it is loaded back into the EPC and verified. If the integrity check fails, the page is rejected. It is important to understand that the operating system still decides when pages should be swapped. SGX does not replace the operating system memory manager. Instead, SGX protects the data during paging process. This means that the OS handles memory pressure and performance decisions, but it cannot see or change the contents of the enclave memory.
Sorry for interrupting you, but for everyone else, when your fellow student is presenting, if you have any questions, you can simply write them in the chat box. Okay.
All right. Another key issue is replay attacks. Without version tracking, an attacker could replace a page with an older valid copy. Even though the data would still be encrypted and pass integrity checks, it would not reflect the most recent state. Version numbers ensure that only the newest version of a page is accepted when it is loaded back. This combination of encryption, integrity, and protection allows SGX to safely use untrusted memory while still maintaining strong security guarantees. The main contribution of this section is a secure paging system that works even when the operating system is untrusted. Evicted pages remain confidential because they are encrypted. They also remain protected against tampering because integrity is verified when the page is reloaded. Version tracking prevents replay attacks, ensuring that only the latest version of each page is used. The result of this design is that enclaves are no longer limited strictly to the size of the EPC. Larger applications can run even if their working memory exceeds protected memory. This is important because without secure paging, SGX would only be useful for very small applications that fit entirely inside of the EPC. By allowing memory to move safely in and out, SGX becomes much more practical for real-world workloads. Enclave measurements. During enclave creation, SGX computes a cryptographic hash called the MR enclave. This hash is built from the enclave's code and the data as they are loaded. Once initialization is complete, this measurement uniquely identifies the enclave. One important thing to understand is that the value represents the exact contents of the enclave at initialization. Even a small change in code or data would produce a completely different hash. This measurement is used for remote attestation. A remote system can request the enclave's measurement and compare it to a known trusted value. If the values match, the remote party knows that the correct code is running and that it hasn't been modified. For example, a cloud service might only send sensitive data if the enclave measurement matches the expected value. If an attacker tried to modify the enclave or load a different version, the measurement would not match the connection and would be rejected. So while secure paging focuses on protecting memory, measurement focuses on establishing identity and trust before sensitive operations take place. Now I'll talk about some strengths and weaknesses of the paper itself. One strength is that the paper clearly explains the overall security goals and threat model. It does a good job describing why the operating system cannot be trusted and what SGX is designed to protect. The paper also provides a detailed technical explanation of secure paging and enclave measurement. The diagrams included are helpful because they make the memory structure and data flow easier to understand. However, there are also some weaknesses in the paper. Some sections are very dense and difficult to follow, especially when multiple low-level mechanisms are introduced at once. The paper introduces many technical terms quickly without always providing enough background or explanation. The complexity of writing also reflects the complexity of the SGX architecture itself, which may make the material difficult for readers who are not already familiar with memory management or process internals. Overall, while the paper is technically strong, it would be easier to read with clearer explanations and more practical context. Before finishing, I want to briefly talk about why these features matter in practice. Secure paging and enclave measurement make SGX useful in environments where the system itself may not be trusted. One major example is cloud computing, where applications run on infrastructure controlled by a third party. With SGX,
Ezra, sorry, I have to interrupt you because we are running short of time. So, do you have any more slides on suggestions? If you have, you can skip these one and go to suggestion slides if you have.
I got the suggestions for improvement in my last one.
Yeah, go ahead.
All right. Um, there are a few ways the paper itself could be improved. Some of the paging mechanisms, as described at a very low level, adding a clear step-by-step explanation would make the process easier to follow. The paper could also include more diagrams or visual examples to illustrate how eviction and loading work. Providing short summaries of key components and terminology would help the readers keep track of the many concepts that have been introduced. And finally, including real-world use case examples would make the material easier to connect to practical applications. And then for my final slide is my thank you. To summarize, these sections focus on two key features of SGX. Secure paging allows enclaves to handle limited protected memory while maintaining confidentiality and integrity. Enclave measurement provides a way to verify the identity and integrity of an enclave, which is essential for remote attestation. Together, these features make SGX more practical and secure for real-world applications.
Okay.
Thank you. I'm happy to take any questions.
Thank you, Ezra. First thing, you prepared a very nice set of slides and following the outline, especially I loved the part where you described the motivation and problem statement, and even the paper idea. So that was like crystal clear
Thank you.
and I mean, from for a undergrad student. That was very nice.
Thank
Okay.
you.
And yeah, now there are some questions. So these questions are for everyone, including Ezra and all other students. So a student is asking, what is the main performance downside of secure paging?
The main issue is overhead. The pages have to be encrypted and decrypted. That means that they have to be verified each time they are moved. Um, and so if this happens frequently, it can significantly slow down the application.
Okay, yeah, that is correct. And not only encrypting, I know the major overhead will be coming from the encryption when you are sending the pages out of EPC to the normal memory, or even sending to the disk, and decrypting when you're bringing them back. But in addition to that, there will be also overhead of doing the integrity check, and also this versioning, like page versioning to stop the replay attacks, right?
Yeah. Mhm.
Okay. Uh,
Al- Although I also had one, it says, why doesn't SGX trust the operating system? Um, it's because SGX is programmed to assume that the operating system could be compromised by either like a malware or an attacker, stuff like that.
That's correct, but here is the motivation or the threat model. Remember, for example, if you are running an application which is too heavy for your laptop or for your desktop, and you rent the cloud server, right? So which
Yes.
has the necessary computing power, but you are renting the computing resources or computing power from that cloud server, but do you really trust the owner of that cloud server infrastructure? Like, let's say you are renting the services from a cloud server provider who is based in China or in some other country which you don't trust, right? Or some any other organization which you don't trust, right? So how can is it safe for you to load your code and your data to that cloud server so that your code can be run and process your data on that server? So no, the operating system running on that cloud server is not under your control, right? So we cannot trust. So that is the reason. Okay. Okay, so we thank you for the presentation. Very nice presentation. Thank you for asking the questions. Questions are also meaningful. I think today's lecture was like I enjoyed it. I don't know about you, but the presentation was nice. The questions during the lectures were also nice. But now we also have the class participation, right, form. So let me extend it because let me extend it by 10 minutes so that you have sufficient time to fill it, and then I will share with you the access code. Okay. Uh, Let me go to assignments and today's class participation form 8, right? It is already released, but let me just only extend its time and give you the code. Okay. I have extended the time, and the code I'm pasting it in the access code and pasting in the chat box. I'm stopping the recording.